Thank you, Deborah, and I am indeed pleased to participate in this. This was a great surprise. As Deborah mentioned, do involve myself in some architectural schools and education, but on a very part-time basis, and no doubt would not have known about this, and nor did I know about the Milwaukee conference 10 years ago, which sounded interesting, and hopefully an event like this might occur in Chicago someday. I hope it does, and hopefully you are successful. Tomorrow evening I know talking about how to keep the ball rolling on this event. I think it's very valuable, and hopefully it'll gain even more participants as well. When Deborah asked me to talk about something here, we got talking about, I asked her whether building information modeling was an issue that people are talking about in education as it is in practice, and of course she said it was. And as it happened, this was before, in the sort of midst of trying to put something together for this year's AIA convention, and that's this product. And I don't know, maybe all of you have one now. They're out there. The AIA was very kind to donate copies for each one of you. It is the Report on Integrated Practice. It is a compilation that was edited by Daniel Friedman. Daniel Friedman was the chairman of the architecture department at UIC and a good friend, and very active nationally in the sort of knowledge area and education. He's just taken up residence in Seattle. He's the new dean at University of Washington in Seattle. In any event, he put this together and was issued at the AIA convention for a series of a 2-day conference on integrated practice on building information modeling. And just sort of ever so briefly, to just review so you know what's all in here, there's a sort of forward by Daniel Friedman, and they're all sort of poster-like. Tom Main has a paper that's really his transcript from a talk he gave 2 years ago in Las Vegas as a part of a panel that he, myself, Phil Bernstein, Pat McLean, and a few others on, that introduced the notion of building information modeling to the AIA in a plenary talk at that convention. So that's been transcribed here, and in fact, I would say that the sort of memorable phrase from that session was his prediction that if you're not using this technology in 10 years, you'll be out of business. In addition, the last chapter, chapter 11, is a CD-ROM. It's an interview by Norm Strong, one of the AIA vice presidents and a partner of Miller Hall in Seattle. An interview with David Mortensen and Greg Knudsen of Mortensen about how they have transformed their business through constructing the Disney Concert Hall, Daniel Lipskin's Art Museum, and ordinary buildings, and really suggesting that this isn't just for the complex buildings. There's a paper by Chuck Eastman on university research, James Johansson on changing business models, Laura Lewinsky and Eddie Kriegel and Bob Berkeley on the roadmap for integration, Renee Chang from Minnesota on suggestions for an integrative education, Kim and Onuma on the 21st century practitioner, my paper on applications in engineering, which my talk borrows from, so it's very helpful that I could hand that out to you because it didn't get into your proceedings. Jim Bedrick from WebCore and Tony Ranella on technology process improvement. And I might add, we talked about this earlier about how contractors and construction managers are potentially taking over leadership role. Well, it turns out that a lot of the leaders of those companies are architects. Jim Bedrick's an architect, but has taken a very important role in WebCore in pushing this technology. Ian Howe from Newforma talking about international developments, Christine Fallon and Steve Hagan, Steve's from the GSA, talking about life cycle. And we and a number of firms participated in a study of business practices there. And then again, the 11th chapter is that CD-ROM. So anyway, I'm really delighted that the AIA was able to do it, and happy that Daniel Friedman was able to pull that together in a relatively short amount of time. And David Mortensen and Greg Knudsen, in a sense, said the same thing, that things are changing a lot and sort of evolving around the building information model. I talk a lot about the sort of applications for building information modeling, and most of them are engineering related, as you might imagine. But there's a lot of things that architects do, and I think that even Ed Allen mentioned that detailing is one that isn't well sort of studied, and it's something that we began to hear that some people are using building information modeling. But there's a lot of calculations that need to be done when you design a building, that either periodically or ideally continuously if it's done in the background, so that you're always aware of how much a building costs, how big it is, whether it's meeting zoning requirements, whether it's meeting natural ventilation requirements, and certainly, ultimately, and the sort of big word that's hanging out there is sustainability. That in order to design a really sustainable building, you've got to keep your eye out on all sorts of things. And how do you do that? And building information modeling is certainly one answer to that question. That's not the only answer, but it's certainly a great tool. And I'm going to sort of walk through a couple of the major disciplines and where things are at with regard to that use of building information technology. And I think that the case study program we saw just in this session before from Montana is very interesting, because they dealt with 4 boards and they really hit on the big items: structure, mechanical, enclosure, there's sort of landscaping site, but fundamentally there are, yes, buildings like airplanes and automobiles have many parts, but the systems, there's a sort of handful of them. If we get right, you're sort of 80% there. That if we can save money in the structure and sort of figure out how to integrate it with the mechanical, it's not so complicated. It's not that many parts, and the rest will fall in. Yes, it would be nice if we could figure out ways to hook up the millwork industry, which uses this technology too, to plug it into the model. But that's a sort of byproduct that would be nice to get to some year, but we've got to start somewhere. And speaking of starting somewhere, we started about in the late 90s, 1999 or 1998, 1999, with structural steel. Structural steel is probably, as I've heard it mentioned several times here, all of the sort of advances they've made. They're an industry that has led the pack, at least in the building world. There's no question about it that they, and there's a number of reasons that I'll go into, but the first project we tried was a steel apartment building that was relatively complex. It was complex in part because it had the bracing in and outside the building, but also used steel as a cladding material in an exposed way. So in a sort of 2-layer system, the red layer on the outside being erected along with the inner layer that's fireproofed. But in any event, that led to our use of this sort of building information modeling, at least for structural steel on Soldier Field. It's a major project that had to be built in 20 months, and it led the team to adopt this technology to improve the prospects for getting steel erected on time and hopefully having things fit together. As it happens, it was a partial adoption. It was pretty much the only thing besides cladding that was done in 3D, and the only reason why cladding was done in 3D was because Premise Delisa was hired to do the cladding, and they have done so many Frank Gehry buildings that that's the only way they work now. And so they were delighted to receive a 3D model of the steelwork and, in a sense, clothe the outside of the building like a tailor and make sure it fit. So things like the precast that you see here, which I'll get to in a second, could have been added into that model, but it wasn't. There were a lot of other things, mechanical, electrical. So it's a sort of case study of partial adoption rather than full adoption. And the lessons learned from that is it's still worth it. It's still worth jumping in and trying something, not waiting until everything's perfect. And these are some examples of, this is again a program called ExDeal, which later has been termed Tekla Structures. It's from a firm in Finland. And it's among a handful of products like this that are vertically integrated within the steel industry that tie together all the way from the design end all the way through cutting and punching and erecting steel. And it really is sort of what you see is what you get. And connections like this, you know, in the past you would figure this out all by hand and do hand-drafted shop drawings, which would be submitted to us for review. And you'd never be able to see how all that stuff fits together, not very easily. And even if you did, you might get it wrong. And it really works. It's transformed the productivity in the steel industry. Piles of steel get erected, get delivered to site. They pick it up off trucks. They lift it in the air. The bolts fit together, and that's a big change in the steel industry. And they're doing it because they've invested so much that they really need to stay competitive. These are other examples of that. These are really the kind of things we saw for shop drawing submittals. Speaking of shop drawing submittals, this is one of them. So this is how we review shop drawings. Rather than look at thousands, tens of thousands really, of piece drawings, you know, drawings of each individual piece with holes cut in it, which are somewhat meaningless because they're not in context. We don't ever look at any of those. We're just looking at things in 3D and then more global erection drawings. And that sort of speeded the process. And this is fundamentally why the steel industry has adopted this. If you're still in business, to borrow from Tom Main, if you're a steel fabricator and you haven't invested in equipment like this, you're probably out of business because your competitors have. Now, in order to run this equipment, you need computers, and you have to get code into that computer. And until programs like ExDeal came along, this is the sort of fallacy of the sort of old way of doing things. In the old way, I would do a design drawing that would be 2D. I'd send it out to bid. Someone would win the bid. Then he'd do a whole new set of drawings called shop drawings. He'd send them back to me. I'd look at them. I'd find any errors I could. I'd stamp it with a stamp that said something like, even if I make a mistake, it's not my fault. Because that's what it says in the contract. And I'd send it back. And at that point, what does he do? He has a whole new set of people sit down and program that machine there. And I never look at that. So if he makes a mistake, which he'll admit is his mistake, this piece of steel comes out to the field, it doesn't fit, and everybody's walking around saying, you know, why doesn't it fit? And we don't know, because that was all part of another process. And as I say, the auto industry and the aerospace industry has figured out how to solve that problem a long time ago, and that is to make a direct path from this model directly to the code that cuts and punches steel. And the steel industry loves that. And you have to understand too, the steel industry has already been doing that for decades. They do it for Bechtel and all those other people for petrochemical plants. They prefer that work, quite frankly. They don't really enjoy bidding on a Frank Gehry project. Or actually, Frank Gehry's, they're okay with Frank Gehry, but a typically complex project where they have to produce the shop drawings, they're not really interested. You know why? This is a manufacturing plant. If they're not running steel through that plant, they're not making money. And when they bid on a project, a multi-million-dollar project, they are speculating on when they think that they're going to have approved shop drawings and steel is ordered and they're going to be able to put that steel into the plant and the workers work on it. When Bechtel gives them a project for a petrochemical plant, they say, here, build it. And they know exactly when they can order steel and they're in control. They have no idea when they're going to get shop drawings back from firms that are working with Daniel Lipskin, people like that. If the shop drawings go back 3-4 times, that means they have a bunch of people sitting idle. So that's the reality of the steel industry, and that's the reality of most industries that produce products that we use to build buildings. And that's why people that can embrace that technology figure out how to use it for you rather than against you. Doesn't mean we have to build cookie cutter buildings. It doesn't mean we have to build we can build great architecture, as been proved by Frank Gehry, but we have to learn how to use that system. So that's a long sort of preamble, but that's sort of the steel industry really has set the stage for this. Now, in the meantime, it's taken a while for the software industry to catch up. The steel industry, this is a typical sort of three-dimensional model that we used on Soldier Field. Back then, 6 years ago, that was not integrated with the modeling side. So like we have been doing for decades, we've had to do that model and start a whole new series of models for representation. As someone said earlier, this sort of set of the analysis side versus the, Kate said that there's this two worlds. Now those are being merged now, at least on the structural engineering side. Tekla has merged it, Revit Structures is merging it. And the notion is that we build one model, we continue to update it to reflect coordination with architecture, mechanical, and all the other constraints. But at the same time, we're able to go away and do analysis. And an example of that is Revit Structure. Here, in fact, how it does it is carries two representations embedded on top of each other. That's fundamentally at least how Revit does it. And there are other ways of doing it, but an easy way to do it is when you put a column in or a floor beam, even if it's sloped, you create a sort of theoretical model, and we've seen some of those today, that's in the background, and those two things are linked. And that's very powerful, such that those two are linked, and so if you change one thing, the other stays up to date. And that's again, a 2D view of that, which is a 3D view of a relatively sort of a mixed system of buildings, not just one type of material. This is Digital Project. This is Gehry Technologies' take on CATIA. We're doing some work with them right now. This is an arena. And again, the practice is certainly moving that way in certain areas. The problem is interoperability. How do we get things from one type of software into another? And Tekla, which we use for steel detailing, we have found ways to get it into architectural desktop. There are ways to get it into Revit. So that, again, wasn't so 6 years ago. So things are sort of moving quickly here, and in a good way. This technology is actually changing the way we work. We now have a group in Kansas City that does steel detailing, that does shop drawings. Now that's something that has not been part of the American practice. In fact, it's not uncommon in other parts of the world. Places like Finland, the structural engineer would be expected to produce shop drawings as part of their work. That there is no shop drawing review process because they're produced, and you, like the petrochemical engineer here, you hand them off to the fabricator to make it. Now, what happens when you start detailing steel is the barriers, or the question of what's structural steel. Is it, again, over the last few decades, there's been, it's steel, no, it's miscellaneous steel, I don't do that. More and more structural engineers are doing miscellaneous steel, they're doing the cladding. and things are becoming more integral. And I think it's so much more evident when you look at a building information model where things aren't abstracted from the structure alone versus the miscellaneous metal. And you begin to see that some steel fabricators would be delighted to fabricate this stuff too, along with the main steel, and erect it all in one piece, again, improving efficiency and actually fit up and things like that. Moving to other structural materials, the precast industry, again, this is fairly recent in the last few years. Precast industry took note, at least in North America, of what the steel industry was doing and said, you know, we got to catch up with those guys. So they put an RFP out. They worked with Chuck Eastman from Georgia Tech, and Tekla won that bid. So Tekla agreed to write a precast modeler that would do pretty much what they've done for the steel industry, which is to create solid models for units and model every piece of rebar, steel embed. If there's steel, model that, but show how precast fits within the global context as well as all of the parts. Use that knowledge that's embedded in the model to run machines that cut rebar and bend rebar. Every industry's got machines that do things. They do. The problem is they're not talking to each other. And that's maybe the biggest goal as to how to hook that stuff up so we're not wasting energy and making mistakes. In Finland, Tekla, which they have a lot of timber up there, Tekla is used to model timber. As you might imagine, there's lots of steel as well. And I think that's the key breakthrough, I think, for Tekla is now it's Tekla Structures, because they'll model any kind of structural material, and both in terms of analysis and modeling, and use it to fabricate things. So it's a very different product, and they aren't the only ones, but I think they're probably the leaders in terms of trying to, in a holistic sense, look at structures, all structures. And in fact, most of the structures I design are mixed systems. I very, very rarely design only concrete, only steel, only timber. It's usually some mix of those systems. And I think a modeling system that addresses that makes a lot of sense. Here's some of the details of steel base plate details where the timber members come together. And then finally, and I think this is the sort of recognition that's going on. I think it's happened some time ago in the UK. The recognition that cladding is yet another structural material that needs to be dealt with, at least from a structural engineering standpoint. There are lots of other energy and enclosure and water and thermal reasons to look at cladding, but certainly from a structural engineering standpoint, it's something that we are getting more involved with. Structural engineers in the United States are getting more involved with. And again, manufacturers like Premise Lisa have figured out how to make money by investing in these kind of software programs and machines that make cladding. Right now, Premise Lisa is using CATIA because they happen to be the product they purchased when they had to do their first Frank Gehry building, or rather Fish, as it happened to be at that time. That was the Fish in Barcelona was the sort of maiden voyage for CATIA and for both Premise Lisa and Gary's office. But this is some manufacturers in Scandinavia that are using Tekla to extrude aluminum and figure out how cladding fits together. I'm going to move on now to sustainability and some of the issues that at least I've become aware of. And it's mainly through, I guess it goes back to Finland. I've been able to go to Finland a couple times and meet some people up there. And on the mechanical side, which we don't really do, but I'm terribly fascinated by, the Granlund, which is a major MEP consulting firm in Helsinki and in that sort of Baltic Sea region. They have developed a complete three-dimensional workflow. They only work in 3D. They use the model that they build initially in part of their design process, and they will build it. If an architect isn't in 3D and BIM modeling and can't give them a 3D model, the first thing they do is build a model. to match the 2D drawings the architect gives. And they'll study daylighting issues. They will use CFD analysis to study airflows and thermal issues in things like arenas. And again, these are very early studies that they do, not sort of in the CD stage. And the net result of all this work, the continuing effort to build a 3D model, is that they work in 3D coordination, that they're constantly working on the ducts and layouts, and those are all linked to analysis programs, just the way structural engineers are using analysis programs that are linked to the model. Every one of those ducts is linked to a diffuser that's linked to a room size that has certain ventilation requirements, and if those requirements change, or if you study different cladding systems, those duct sizes will change. So they have fully invested in that, at least in Finland. I'm not aware of any body in the United States that's as advanced as they are. They also do a lot of 3D life cycle studies. Now, I know Autodesk is working hard on getting their building services modules for Revit up and running that would link to analysis programs. But these are programs. These are some images I've got from Phil Bernstein at Autodesk on the kind of full coordination between architecture, structure, and mechanical that they're working on for Revit building. And we're adopting Revit Structural at Thornton Tomasetti. So, in fact, I've been very surprised the last 6-7 months. And I've obviously been very involved in this issue for several years now. But the acceleration of clients of ours talking about it, doing it, wanting us to do it, is the last 6 months has been nothing like the previous couple of years. So I think there is an acceleration now that if you're not getting ready for it, it's definitely coming. Things like the GSA, we're starting our first GSA project that's demanding the use of 3D. We're actually using Revit in that case. We didn't have to be Revit. But you don't have to use one suite of projects. That's one suite of software. That's the sort of big advantage coming out now because of these open standards that are being promulgated now. Here's an example from Tekla of ArchiCAD architecture. There's the Tekla Structures for the precast and things like that. And then there's a program called MagicCAD with the ducts that Granlund uses. It's a program out of Scandinavia that apparently is not available anywhere other than there, but that's the program they use that's linked to the analysis programs. And so fundamentally you have these separate models and they're all combined together. In this case, a program called Navisworks, which is a sort of a Swiss Army knife of a program that will accept any standard and basically do class checking. Firms like Mortensen are using Navisworks to check how different systems come together. And I think that's the other thing that's going on is the notion that an architect or a building modeler or someone else is going to model everything. While they could do that, what's really going on is that we are going to do our part. Hopefully we'll find some mechanical engineers in America that will do that part. But that's really been slow. It's been hard to find people that are, there are firms doing it, but they're doing it reluctantly. And of course the architect's working in 3D and they're sort of brought together. And I'd say there's more work to do on that, but we're much further than we were 5 years ago. And I have no doubt that 5 years from now, there'll be great progress made. And then finally, Bentley, which I think has a bigger presence in Europe, particularly Europe. Firms like Norman Foster, Nick Grimshaw, and others use MicroStation. There are a few here. Morphosis uses MicroStation, but it's pretty thin. It's mostly used in the transportation area. Yes, there are some firms that use it, but as you can see here, this looks like more of a fairly heavy industrial project. I think this might be in Japan. But anyway, I got this from Bentley. as an example of their systems integration. It's very sophisticated. There's a lot of good software out there, and much of it actually will talk to each other. Maybe not fully. Maybe you'll lose a few things, but it's a good time. Well, that's design, but as I said briefly earlier, I think it's more than that. If we just do that and see that things fit together, we're not taking full advantage of everything that the building information model has to offer. And smart contractors like Mortensen and Webcor are begging for these models because they will use them to fairly quickly determine what the cost of the building is, because all the areas and volumes are there. They can link them to spreadsheets that determine building costs. Virtual design and construction. Martin Fisher at Stanford has been a leader in this area of linking 3D models to time and now cost, so 3D, 4D, and 5D modeling. And then finally, just-in-time construction. The nice video we saw today of construction in Ontario was wonderful. A lot of that is choreographed. You want, when you're going to do big pieces of assemblies like that, you've got to know when they're coming. And what's nice about the steel industry more and more is they're keeping track of that steel all the way through the life, the sort of supply chain. It's sort of supply chain management. And so just-in-time construction. I'm going to give a brief example of ours that we were able to work with one of the graduate students from Stanford to spend a last summer with our team in Chicago, working on the infamous Block 37 in Chicago that finally is going forward. We're down in the hole right now. It's very complex. It's a whole city block in the heart of Chicago that's it's in the middle of 2 subway lines and utilities, and we're going down about 50 feet. We're the structural engineers for the entire block, which is one building, but it's got 3 different architects. So we're collaborating with 3 different architects, and there aren't any expansion joints. So it's interesting, some of which are sitting on top of other pieces. So, and we're doing something that more common in cities like Boston, up-down construction, where we're digging down, tunneling down, and digging up and building up at the same time. This is the full city block, and we're going to put a slurry wall in around here. We're going to put a subway station through the site to connect up the red line with the blue line. And this will actually be, eventually, when everything's built and everything's hooked up, a high-speed train line that will take people from nonstop from O'Hare to downtown to Midway. Because those 2 ways to get to the airport currently don't hook up. This will be the thing that hooks them up. So in addition to our work, there's also going to be tunneling that goes on outside the site. And so there's a lot of geometric coordination, a lot of transfers. And so I proposed early on that we think about using 3D for this. As it happens, we didn't use it fully. It was sort of typical of a lot of these things now. If you have contractors that don't know how to use it, owners that have never used it, they're suspicious. And so we probably have a lot of work to do in terms of education. This is the kind of, but as you can see, we're all working in 3D. This is a ETABS model of, and fundamentally it's this whole series of concrete cores and structural steel framing among, here's Ralph Johnson, here's Gensler, and here's Solomon Corwell Benz up here. So it's all one building. And Peggy Ho from Center for Integrated Facilities Engineering at Stanford did a 4D model. We all agreed, notwithstanding the fact that we weren't going to take it all the way through, that we do some early schematic design work, where she would study this notion of how do you tunnel, this is all dirt magically disappearing in chunks, and how do you do that while you're sort of building up? See, there's not a lot of up right now. But now you're beginning to see some sort of up. Actually, there's about a 4-story retail area around here that's going up as well. And there's the second one which shows the subway connector, one of those subway connectors, how we're going to sort of tunnel out through that and sort of create that sort of stuff. So that there's a sort of whole area of construction management, but how that interfaces with architecture that very few people are researching right now. I would say Stanford is the sort of leader in that right now. The reason that this is all valuable, building information modeling is valuable for them because they get information-rich 3D models that tell them a lot of things about that material, and they can add more information as they go. And so, what's next? Well, education. I'm very delighted to participate in this. I think that this is, as someone else said earlier, a process that's coming from owners. The Construction Users Roundtable has sort of demanded that somehow we begin using this technology. Owners like the GSA are saying we must use this kind of technology, and it's working its way through the profession and through education. There's a lot of contractual insurance issues, and that downstream use of data. What if it's wrong? Those kind of questions are out there, but the probability of having it right is in a way much higher than the current system. So that's why we have to keep figuring out how to sort of get there. I plopped this into there. I was seeing a couple of different things today, which I thought were wonderful tools, and I think that the tools that we use, not just in practice, but we teach our students with, in a way, it would be delightful if they were as easy to use as this. This is, for those that don't know, and I'm sure many of you do know about this, but this is the U.S. Military Academy in West Point's bridge contest, and it is a very simple software tool. You're allowed to build a bridge and test it. You drive the bridge across, the truck across, and see if it works. And it deflects, and it gives you all the things we were talking about earlier today. That sort of feedback about stress. You can sort of instantly see what's going on. And of course, here I've taken out one of the members just to see if it will work, and it doesn't. So, and that's for children. This was designed for grade school kids and high school kids to learn how to design things. And they have interesting features on this thing. As you build your bridge, you're keeping track of cost. And because the competition is who can build the cheapest bridge that still works. And that's what I meant about you need, and that's a very hard thing to do. If you tell a design student that, show me 5 options, and by the way, tell me how much they each cost, and that's kind of a pain to sort of do that at the end. But what if it were just doing it in the background, just the way spreadsheets do? That's what these guys are doing. And you make decisions about what you can change these members out, and you see that one's not working, you make it a little bigger. And so I think that I think once we implement this and that information is laying there in all these projects, both design projects and case study projects, that our creative architects and engineers are going to find cool things to do with them. They'll continue to find ways of extracting that information, doing quick studies, and add to the analysis phase of design. And so, in conclusion, to borrow what Ed said yesterday, let's use BIM to get the form right. Thornton Thomas City, for those of you who don't know, we're kind of mostly up here, lots of East Coast presence. I'm out here in Chicago. Some of our offices help out with architecture schools. We're delighted to do that. If you see one of your cities near one of your colleges and you're interested in contacting somebody there, come see me. I'd be delighted to hook you up with somebody. Thank you very much. We have 10 minutes. I'll take some questions. I guess do you have any questions?
Joe, can you elaborate? I'm just curious because I'm encountering it for the first time. How that up-down building process works? Is that too much?
No. I'll do it real quick. And it's not the first time it's happened, although there's a couple in Chicago that's done it. The most, probably the ones I know about are more in Boston, Rose Wharf, 75 State Street that Skidmore did. Fundamentally, you put, everybody know what a slurry wall is? Okay, good. So you put a slurry wall in, and then you put caissons in, or piles, and you fundamentally you're putting your columns in first, all the way down. In the case of, there's two ways to do that. One, you can just treat the caisson, the 6-foot diameter shaft, as a column. Not very efficient, but it's cheap. Or you can drop a very heavy steel column down that and leave it there and come back and chew away at it. So fundamentally, you're standing on the surface, you put all that stuff in, and then you put your ground floor in.
So you're casting on grade?
Either cast on grade or erect steel. Our ground floor is going to be steel, but you could cast on grade. Then you go down and mine underneath it with mining equipment, like bobcats and mining equipment. It's expensive, so this isn't something. The only reason why you do this is, well, there's two reasons why you do it, is to save time, which is money, and so even though you're spending more real dollars, you're saving interest because you can build quicker. You don't have to go down 50 feet and come back up again. And then once you get your first floor in, then you're building up. You can just keep going up while you're tunneling down. And usually the parking garage is the sort of way low on the sort of critical path on project. Nobody, there's very little finishes. All the finishes and mechanical systems are up above, so you don't really care that it's going to take you longer to build a basement. It's that you're building it concurrently. And so you go down, you level off the floor. There's a couple of ways to build the floors, but the cheapest way, and the one most used, is to pour a mud slab where the bottom of the slab is. Then you cast your slab, and then you go down below, and you do the whole thing over again. And you just keep working your way down.
How many levels below grade?
We're going down 4, about 50 feet. Yeah.
So on the cost model, how many connection?
I've been in a meeting with NIST and some other people. Chicago will take a long time, but the city of New York was interested, and there are places in the world like Singapore and Denmark that are requiring it now. And they're using it not for structural analysis code checks, but there are a lot of programs, not a lot, there's some programs out that do exit analysis to make sure that you don't have dead-end corridors and that you've got the proper spacing. And that's sort of, I guess, in the world of BIM, a relatively trivial calculation to make for, the types of rooms, the occupancy, exit width, all that stuff. And so that's something that, as you say, I think it's coming. As I say, I've heard that places like the city of New York are very interested in it. I mean, in a way, it's a little surprising that, we do very sophisticated structural analysis, but when it comes to fire engineering, as an example, it's very low tech compared to what we could do. That's a science in other parts of the world. Timed exit analysis, we always sort of hew to the sort of rules of thumb versus very sophisticated programs that could be, in a sense, could result in more safety. The problem is, in my view, because having talked to Australia and England and a couple other places, is if you go to those areas that are using more sophisticated fire engineering, you're going to find that the people in those agencies for the municipalities are properly trained fire engineers and smart people, and they're able to understand the issues that are being presented in a sophisticated building. That's typically not the makeup of the municipal departments in the United States. Nor do we have nor do we have actually the universities that are training those people. As it happens, the University of Maryland happens to be one of the top 2 in the country in that area. In fire, booster, I may have this wrong, but somebody can correct me if your field's slighted at your university, but I think Worcester, Polytech, in Massachusetts and Maryland are pretty much it. Whereas you go to Australia and England, and you get 10, 11, 12 institutes that are as big or bigger. Yeah.
So I wonder if you can speak to the applicable building types or building scales. And is there any building size that wouldn't be appropriate for you to do?
I don't think so. I do think that they I think they're going to be applicable to all scales. I think that some of the sort of, I don't want to call it manufactured housing, but I would call it the sort of developer single-family residential work in the United States. That's the vast majority, big part of the construction market. They're adopting this technology for just-in-time. It's all the stuff that I talked about, and again, stuff that architects aren't designing typically, but at least not the traditional sort of path. So I think that it's all applicable. Yes, sorry.
I don't know too much about it, but I understand that the typical IA contract has long had a clause about means and methods that the architect says what it looks like, but not how to build it.
Yes.
That's the contractor job.
Mm-hmm.
Now, it strikes me that the potential of these technologies can integrate a how to build it component into the what it looks like component. And I'm wondering if you have any thoughts of whether that is an anachronistic idea that the architect should or engineer shouldn't get involved, and how it relates to this whole new technology.
Well, that's a difficult question. First of all, that particular segment of the AI contracts you're referring to is an attempt to keep us away from lawsuits resulting from construction accidents, which we get pulled into anyway. but we try to, and we usually win, not. And it's true though, if you walk around a construction site and you make statements like, you shouldn't be doing that because that looks, it's incredibly unsafe. People are taking notes down, and when somebody gets hurt, you'll be hauled in to court, and that's where that comes from. So let's set that aside, though, from the real issue of how do you build something. And I think I was delighted to see this exhibit by Vaclav Zalewski out here. He's clearly somebody that gets it, that understands how things go together, because you can't design that stuff unless you think about the process of how do you build it. And we do that with, I would say, with most of our sports projects, big arenas, and you can't design something without thinking about the process by which we do it. Now, we do it collaboratively, though. We have some ideas, but we'll sit down with the contractor, the CM, and sometimes we'll sit down with steel erectors and think about how we do that. I'd say we have a growing proportion of our work that's design-build, where we work directly for, let me call it a developer, really. It's the person who is responsible for building it. And we very often, early in the process, sit down and figure out, answer the question, how are we going to build this? There's one of my favorite clients is an architect who is also a developer, who is also a contractor, and also an architect, of course. He designs all his work. In fact, he only designs for himself. He doesn't design for other people. And he is very successful. Good news for me is he doesn't have structural engineers on staff, so he gets to hire us. And he also taught for many years at IIT. I think he might still a little bit, but he was a tenured professor at IIT. I think we've got to broaden our definition of what an architect is and what an architect does. Because there may well be an architect who wants to take the risk to go out and build stuff. And you know what? Those buildings are going to be very well put together because that's going to be part of the design process. And I think some of the best buildings have that extra quality of thinking about the process. Yes?
How close do you think we are to a point where software is capable of doing so much of the mathematical part of the structures that the structural engineers will only be concerned with the form and they'll let the software take care of the rest?
That would be a nice time, but no. I think that I don't think we're there, and I think that it's a continuing process. It's not that we dream up a form for the building structure, and then we put it on autopilot, and out the other end comes steel. I think there's still a process of iteration, of coming up with an idea and needing to distort it because of some issue that arose, and we have to sort of keep on top of it. I think one of the big issues that's going around now in the industry is that we need to push all of that up closer to the start time rather than waiting till construction documents. That more of that input needs to come earlier, and it's forcing us though to want to get at that mathematical analysis more quickly, more directly, right from the work we're working on.
Do you see the structural engineering profession ever going back to dealing more with form? Or,
I think so.
I see structural engineers coming out today who have no concept of form or how a building goes together, but certainly can write a computer, quite
well. That
do you see that? I mean, I don't see European engineers doing that as much, and I know it's maybe just us looking over Europe and wondering why our engineers aren't as creative as theirs. But do you think, or do you disagree with what my statement?
I don't disagree with you. I think we have a serious problem. I think I maybe even said it several times already that I think that the issues you're struggling with here in group of how do we teach building technology within the context of a design school isn't even being debated in the engineering world. There's no rooms full of people like this talking about how we teach design in the engineering world. And so that's a serious problem. And the sort of modest proposal is that I think that some architecture schools might want to consider teaching engineering design collaboratively with their architectural design. Maybe creating a situation where someone that starts out in architecture, like I did, might end up in graduate school in engineering design. Because I think that all of those issues of form are not, there's no way we're going to take on the sort of colleges of engineering of America to change the way they do things. At least I don't, that's not one of the things I have on my list of things to do with the rest of my profession. In fact, I have much greater optimism that in fact there'll be some schools, there already are some schools like the University of Illinois at Urbana that teach that structures option, and we have structural engineers in Chicago that go through that program, and they're good structural engineers. I wish there were 20 more programs like that. Okay, we'll see you all down in Washington.